Hi, welcome to the second video on electron paramagnetic resonance, which will be focused on Hyperfine splittings. We have seen before that electrons have dipole magnetic moments, and these dipole moments can align in an external magnetic field, and therefore there are two possible energy levels for one electron that are defined by a spin +1/2 and -1/2, and these energy levels are split by a magnetic field, and we can induce transitions between those energy levels and therefore detect a signal that is related to basically the electron resonance phenomenon. Electrons can also split their energy levels by interactions with any magnetic field, and one such magnetic field is the one that certain nuclei have, like hydrogen, nitrogen, phosphorus, fluorine, and many other elements have certain nuclei with magnetic moments. So the interaction between the electron and nuclei magnetic moment produces splittings of the energy levels of the electron, which we can detect in an EPR spectrum. Those are called hyperfine splittings. So there are many possible situations. For example, in the top part we see that there's an electron that has a spin up. Because of the negative charge of the electron, then its magnetic moment will be pointing down. So the north pole of the magnet, which represents the magnetic moment of the electron, points down. So, but nuclei with positive charge have a spin which is parallel to their magnetic moment. So for example, when two magnetic moments or dipoles are parallel to each other, like in this scheme, if their north poles are opposed, they will attract. And if their north poles are aligned, they will repel. So this is basically a side-on orientation of the two dipoles. So basically this means that they will attract when they have opposite orientations of the dipole moments, which means that they have parallel orientations of their spins, because again, the dipole moment for the electron spin is opposed to its direction. So for the electron that has a spin +1/2, in this particular orientation of the electron and the nucleus, the nuclear spin +1/2 will cause a decrease in energy, and the nuclear spin -1/2 will cause an increase in energy. So this depends on this particular orientation. For the case of the spin down electron, we have the opposite orientation. So basically ms equals -1/2 and ms equals and mi equals -1/2 will be the lower energy state for the side-on orientation of these dipoles. If we on the other hand have that the electron nucleus direction is parallel to the magnetic moments, not forming a 90-degree angle as before, we will see that then the parallel orientation of the magnetic moments, I mean both north poles pointing down, will produce an attraction. So this means that the electron and nucleus spin point in the other direction. So for example, in this direction, for the ms equals +1/2, the lower energy state will be with mi equal -1/2, and the opposite case will produce a repulsion. So the two north poles of the electron and nucleus magnetic moments, if they point to each other, they will repel, and that will be the situation of parallel spins. So from these two figures, we see that there's a relative orientation dependence of the attraction or repulsion of different spins, which will be translated into a sign plus or minus in the interaction between those spins when we see the spin Hamiltonian for the hyperfine splitting. Lastly, there's a case where the electron spin and the nuclear spin are in the same position. How can this happen? The nucleus has a certain mass, a certain radius and volume, and the electron is delocalized in an orbital. Certain orbitals, particularly 1s, 2s, 3s orbitals, have a non-zero probability of being on the exact position of the nucleus. So the electron is distributed in a region of space, but it is partly going through the nucleus. So the electron can be actually in the nucleus, but it doesn't happen for orbitals. For example, for an atom, electrons in p orbitals, d orbitals, etc. do not have any probability of being in one nucleus, but the s orbitals do. If, on the other hand, we have a molecule, we can easily have that the p orbitals for a certain atom, for example carbon, which may contain an unpaired electron, can have a non-zero electron density on the nuclei of adjacent atoms, like a hydrogen. For example, we can have a CH fragment in a molecule, which is a radical, so the hydrogen can experience a small amount of electron density on its nucleus that comes from orbitals in surrounding atoms. So this can cause a hyperfine splitting. So what happens in this case where the electron is exactly in the position of the nucleus? The lower energy configuration is for the two magnetic moments to be parallel. So that means that the two spins, the electron spin and the nuclear spin, are more stable when they are anti-parallel. So we can see this in these graphs. When the ms equals minus 1/2, the lower energy state is with mi equal plus 1/2. And vice versa, when ms equals plus 1/2, the lower energy state is mi equals minus 1/2. So these are two formulas that describe what I have been discussed below. There are several contributions to the hyperfine splitting of an electron by a nucleus. The first one is the Fermi or contact interaction. Basically, it has a series of constants. It involves the G factor of the electron. Beta E is the Bohr magneton of the electron, but also involves a G factor of the nucleus and the Bohr magneton of the nucleus. We are not going to get concerned right now with that, but those numbers are tabulated for basically all normal or known isotopes, and this can be looked for. Then we have a product, a dot product between the spin operator S and the nuclear spin operator I. So this is the part that allows us to calculate the different energy levels depending on the orientations of the electron and nuclear spin. And then there's this psi 0 squared. So this is the value of the wave function of the electron at the position r equals 0, which would be the nucleus. So this is for an atom. In a molecule, we would replace this 0 by the position of each nucleus that we are interested in calculating. And this is the squared, the modulus square of the wave function is basically the electron density. So orbitals which have a large electron density on a certain nucleus will experience a larger Fermi or contact interaction. This interaction is in principle isotropic. It means that it is the same in all orientations of the measurement, all orientations of the external magnetic field with respect to the molecule. Then there is this other interaction, the magnetic dipole interaction, which has this slightly overwhelming formula. The dipole interaction basically tells what I have been telling in the first two slides, that the magnitude and sign of the dipole-dipole interaction between the electron and the nucleus depends on the relative orientations of the dipoles and the vector that goes between the electron and nuclear dipole moments and the direction between those moments. So we can see here that we have a term S dot I, which is similar to the contact interaction term. We also have the nuclear and electronic G factors and Bohr magnetons, and we have these terms that basically are the dot product of the spin times the unit vector that joins the electron and the nucleus. And also we have this dot product between the nuclear spin and the unit vector that joins the electron and the nucleus. So these dot products are the ones that define orientation, because dot products of two vectors have a magnitude that's a scalar product that depends on the magnitudes of the vectors times the cosine of the angle between those two vectors. So that when you have a cosine of an angle, that's when you have directionality, you have anisotropy. So this term in brackets is the one that defines that you have different signs for the magnetic dipole interaction depending on the relative orientation of the electron and the nucleus with respect to their magnetic moments and relative to basically the external magnetic field that we use in the measurement. Also, there's a term here that's dividing. This is μ0 is the vacuum permeability, h is Planck's constant, and r cube is basically the distance, not the vector, but the modulus of the distance between the electron and nucleus. So this basically tells us that the dipolar interactions falls off with the cube of the electron-nuclear distance. So of course, electrons which are closer to a certain nucleus will experience a stronger dipole-dipole coupling. So we are going to disregard for now this part of the Hamiltonian, the magnetic dipole interaction, and there's another interaction which is the spin-orbit coupling, which is very important when you are trying to calculate hyperfine splittings involving transition metals or lanthanides or different molecules. The spin-orbit coupling is an interaction between the nuclear magnetic moment and the orbital magnetic moment that many electrons have. So, but we are not going to discuss that right now. This is a more advanced subject. In principle, the hyperfine splitting is anisotropic because of the dipole interaction and also because of the spin-orbit coupling. Sometimes you have 2 or 3 values that define the hyperfine splitting in different directions. But for now, to start studying hyperfine splittings, we are only going to focus on isotropic systems. So systems where, for some reason or another, all the anisotropy is averaged out. For example, if you have a small organic radical in solution at room temperature or even below, it may be rotating very fast in all directions. So because of that, several anisotropic quantities completely average out. In the case of the dipole-dipole interaction, the average of a pure dipole-dipole interaction is 0. So you have positive values in 2 directions and a negative value in another direction that completely cancels those positive values. So the average in all directions is 0 for the pure dipole-dipole interaction. So that causes that the remaining interaction that we always see is the contact or Fermi interaction, the isotropic hyperfine splitting, so that we can measure. And this is very useful because we can use this measurement of this magnetic interaction to determine the spin density of electrons in different nuclei, and we can correlate that with calculations or with Huckel molecular orbital diagrams or other types of analysis of the spin distribution in a certain molecule. So for understanding the chemistry of organic radicals, the hyperfine splitting that comes from the Fermi interaction is very important. So now we are going to see more or less what happens with different cases for the totally isotropic interaction. So we have again the contact interaction here, and we are assuming that we have an electron spin 1/2 interacting with a nucleus with spin 1. So this nucleus has three possible states: +1, 0, -1. This could be, for example, a 14 nitrogen nucleus. There is a certain splitting, and the electronic transitions that we see by EPR, not by NMR, so are only between different orientations of the electron spin, but they have to conserve the orientation of the nuclear spin. So when we do EPR, the frequency that we apply to our sample doesn't cause any nuclear transitions. In NMR, we produce nuclear transitions and we would flip the nuclear spin, but in this case, the nuclear spin is the same. So basically, the transitions are from Mi -1 to Mi -1 and changing the ms, and the same for the other Mi values. So basically, this causes to split our signal into three. So here are the three signals. In the first video, I showed that the signals were an absorption, but in EPR, it is usual for instrumental reasons to measure the derivative of the absorption. So the derivative of the absorption has this shape that has first increases and then decreases. So I'm going to explain on another video why that is, and discuss some instrumental features. But for now, let's just say that all our signals will be derivatives of absorptions, and they look like these signals. So in here we will have three signals due to the hyperfine splitting of the electron spin by a nucleus of spin 1. And the contact interaction, we can simplify it in this term to be a term A, which is basically a empirical constant that contains all previous values. It contains all these different values like the G factors of the electron nucleus and the spin density on the nucleus. And the S.I scalar product, we can replace it in the isotropic case with only the Z projections. So basically we define our axis of quantization, that is called, to be in the Z direction. Basically we don't need to concern ourselves with the X and Y directions. This is a valid approximation for isotropic systems. So again, this is the contact Hamiltonian for the isotope splitting, and in order to analyze more in detail what happens, we are going to choose the simplest possible system, which is a spin 1/2 for an electron and a spin 1/2 for a nucleus. So again, we have transitions that don't change the value of the nuclear spin. So we have four possible states. These states are defined using Dirac notation as kets. These are called kets, that has ms equal +1/2, mi equals +1/2, ms equals +1/2, mi equals -1/2, etc. So we list all four possible combinations of the nuclear and electron spin. Luckily, when we apply a Hamiltonian of the type SZ times IZ to this ket and bra, which is ms mi, ms prime, mi prime, we can separate this into the spin part, electron spin part, and the nuclear spin part. So why did I put m prime? Basically what I'm doing here is calculating a generic bracket in which ms can be +1/2 or -1/2, and m prime s can be +1/2 or -1/2. So I'm considering in this simple notation all four possibilities. I could also have been using +/-1/2 and calculate all possibilities. So basically we can separate the bracket that is a product of ms and mi quantities. We can separate them into two brackets that are one for the electron part and one for the nuclear part. So this simplifies our problem. So if we calculate the value of S on m prime s, we get m prime s times the same ket, and therefore this is a constant m prime s that goes outside the bracket. So we get m prime s times the bracket of ms m prime s, and we have the same for mi. We get m prime I, which is a number, is either plus 1/2 or minus 1/2 in this case, times the bracket of mi m prime I. Okay, so what are the values of these brackets? Because of the orthonormality of the different quantum states and also spin quantum states, if ms and m prime s are the same, if both are plus 1/2 or both are minus 1/2, this bracket will have the value 1. If they are different, it will have the value 0. The way to mathematically describe these conditions is through the Kronecker delta function, which is a function that says its arguments, in here ms and m prime s, if they are the same, the Kronecker delta function is 1, and if they are different, the Kronecker delta function is 0. So the Kronecker delta is the discrete version of the Dirac delta function, which applies to continuous functions. So basically we get that the whole effect of the Sz times Iz Hamiltonian on the different bra and ket possibilities is equal to m prime s times m prime I times the deltas. So the deltas imply that ms and m prime s have to be the same value. So we can replace m prime s by ms, and we can replace m prime y by my. And basically we see that the contact interaction is this Hamiltonian multiplied by a number which is a. So numbers can be simplified and put in front of the brackets with no problem, because numbers commute with all operators that we use in quantum mechanics. So if we remember that in the last video we saw what were the energy levels, ms energy levels of an electron in an external magnetic field that gives rise to these straight lines which are linearly separating with the magnetic field B, we saw that the energy separation was mu b times the g value of the electron times the ms value times the external magnetic field, B or B0. So now we can add the hyperfine splitting interaction. So we have two possibilities for ms and we have two possibilities for mi. So we can calculate there are 4 energy levels. And for ms equals plus 1/2, we'll get the plus 1/2 in front of the mu b times g times b0. So we have it in the first energy level and in the third energy level. For ms equals minus 1/2, we have the minus 1/2 in front of the mu b times g times b0 term that goes into the second and fourth energy levels. And then we have the two possibilities for mi. So basically, if we multiply 1/2 times 1/2, we get plus 1/4, and this multiplies a. And if we multiply plus 1/2 times minus 1/2, we get minus 1/4. So these are the 4 possibilities. For each of them, we can see here that ms and mi with a positive sign will give a positive sign here. So this is one of our energy levels, which in this case will be the higher energy level because it has only positive quantities. So it will be this level on top. And for example, this other level, ms equals plus 1/2, mi equals minus 1/2, it has a 1/2 in front of the Zeeman part, and it has a negative value in part of the hyperfine splitting. So basically it would be this energy level here. And we have the other levels which have basically opposite signs. So I encourage you to actually do this calculation. So you have to, in this formula, replace all 4 possibilities for the 2 for ms and the 2 for mi and actually calculate these energy levels. It is very easy, but it is a good practice to know how to systematically calculate these things. So basically we have 2 transitions between ms equals -1/2 and +1/2 that keep the same value of mi. And we see these 2 transitions here that occur at different values of the magnetic field, because basically the electron energy levels have been shifted, have been separated, or they have gotten nearer because of the effect of the hyperfine splitting. If we calculate the difference in energy levels between the up and down electron spin states, we have the delta ms equal +1. So we are subtracting the +1/2 and -1/2 spin, but we keep the same value of mi, because again, in electron paramagnetic resonance, we are inducing transitions between electron spin states. So we keep the mi equal +1/2. We can subtract the 2 energy levels in the previous slide, and we will find that the delta energy level is mu. This should have been mu sub b, the Bohr magneton, times g times a magnetic field that we will design as mi equal +1/2 to imply that this corresponds to the mi equal +1/2 orientation of the nuclear spin, and we'll have plus a/2. Why? Because we have done basically a/4 minus a/4. So you have to go again and check with the previous energy levels. And for the mi equal -1/2 case, we have the same. So now this magnetic field value will be different, and we will have minus a/2 because we have subtracted minus a/4 minus plus a/4. So again, we have the same transition. So what we have calculated is the difference in energy values for these 2 states, the top and the bottom one, and for these 2 states that have basically the b values will be different. If we equate the delta E between the different levels to the energy of the electromagnetic radiation, h nu, we have again h nu equals mu times g times b, that depends on mi, plus a/2, and we have the same with b for the mi equals -1/2 minus a/2. So we can simplify and obtain the values for the magnetic field b as h nu minus a/2 over mu b times g. I got the b back here. And the other magnetic field for the other transition will be equals to h nu plus a/2 over mu b times g. Again, I encourage you to do these calculations yourself. These are quite easy, all these steps, but it is good to actually do the calculations and not just trust me. So I don't have good animations like 3 blue, 1 brown, or Mathologger, or other actually excellent YouTubers. So basically we can calculate the difference in delta B between these 2 energy levels, and basically the h nu over mu b times g will cancel out, and we'll get minus a/2 minus a/2 will give minus a. So here I'm taking a absolute value to simplify things, and basically what this tells us that the magnetic field separation between the 2 resonances, which is what we actually see in an EPR spectrum, we will call it delta B for now, is equal to the hyperfine splitting A that went in the Fermi or contact Hamiltonian divided by the Bohr magneton times G. There are other constants. There's one more constant, but we will see it later when we actually calculate things. So for now, I just want to show you the concepts. This means that the actual separation of the two hyperfine lines will not only depend on the hyperfine value A, but it will also depend on the G value. So it will not be the same. And the hyperfine constant A is an energy term that is usually expressed in something like megahertz or wave numbers, or it could also be expressed in joules or any other energy quantity. But delta V is expressed in magnetic field units, either in Gauss or in millitesla or in Tesla. So for example, if we measure in a certain spectrum that the separation between the two lines is 5 millitesla, that is not the correct way of expressing that quantity. We have to multiply it by the G value and by a couple of constants like the Bohr magneton and the Planck's constant, and we have to express that in megahertz. So for a G value of 2, which is common for many organic radicals, we should multiply the separation in millitesla by roughly a factor of 30. So a hyperfine splitting of 5 millitesla in a spectrum would roughly be 150 megahertz. So this is all for this video. We are going to see in the following video examples of hyperfine splittings of different systems, how many lines we observe, how to interpret that. It will be a more practical video. Thank you very much. Please, if you have found this useful, like and subscribe, and share it with other people that you think they may be interested. Thank you very much.